Okay, our next talk presenter is Dr. Matthew Palmer. He's the head of science and digital innovation and marine autonomy in Plymouth Marine Laboratories. His talk will be about the UK National Centre of Coastal Autonomy, a centre of excellence for coastal marine autonomy. So please join me in welcoming Dr. Palmer.
Hello there. Can someone just confirm if they can see my screen, please? Hello?
We're setting the audio up. Just a moment, Doctor.
Hello?
We hear you. We hear you,
Okay.
Dr. Palmer.
So can someone confirm that they can see my screen, please?
Yeah, we can see it.
Excellent. Well, thank you very much to our hosts for the invite, and my deepest apologies to them and to the audience for not being able to join you this week. Unfortunately, I've got a slip disc that I'm currently having problems with, and that got worse last week, so I unfortunately couldn't make the trip. I'd like to talk to you today about a new initiative that's coming through from a partnership initiative called Marine Research Plymouth, and this is the National Centre for Coastal Autonomy. And that's a partnership between Plymouth Marine Laboratories, where I now work, the Marine Biological Association, and the University of Plymouth. And I apologise, but I've started at the end. So try not to look. I'll give away all the secrets. Right, there you go. So I've recently joined Plymouth Marine Laboratories as head of science for their digital innovation and marine autonomy. And I've worked with quite a few of you in the past in my previous role as chief scientist at the Marine Autonomous and Robotics Systems facility in Southampton. So I wanted to take a bit of an opportunity here to introduce this new initiative, but also explain some of the great things that are going on within this Plymouth partnership. And thanks to the previous speaker, Professor Sharma, who's already provided a really nice background to some of the work going on at the University of Plymouth as part of this partnership. So as Professor Sharma mentioned, the Plymouth is designated UK's Ocean City, and that's really based on its really long history of connection with the ocean, and it's particularly relevant to its marine research. So Plymouth actually hosts the largest concentration of marine scientists in the UK, and there's a whole array of different activities in that space, all the way through from marine research, social science, economics, engineering, and many other things. One of the flagship programs within our oceanographic capability is the Western Channel Observatory. And that's a large program that's run by Plymouth Marine Laboratories that can date observations in the Plymouth, the waters off Plymouth and the coastal ocean environment back to 1903. And that presents one of the longest running time series that we have available. Research there is ongoing, and we've also complemented that with an additional station at L4 about 35 years ago, 1988. And there's a whole host of different activities going on in that space. And I was going to explain where Plymouth was, but like I say, I think you've already been introduced to that nicely earlier today. I think it's worth noting its location relative to this very broad shelf sea that surrounds the Northwest European shelf. So we are several hundreds of kilometres away from the shelf break in a highly active sea, and there's a significant tidal range there. So it's a highly dynamic environment. I think one of the key things that we're worth drawing on relative to that long-term observational capability is the large amount of infrastructure, skills, talent, people, and equipment that's required to actually keep that sort of sustained capability going. And I think that's really where our focus is and has been historically in terms of trying to identify where we can best use autonomous solutions to better undertake our science. And if we look at the broad range of activity that we're currently doing, this is just the Western Channel Observatory. That's just one node of that Marine Research Partnership, Marine Research Plymouth Partnership. We can see that there's a whole host of different disciplines in order to try and consider how we actually might best deliver our science package. So a more recent activity is the formation of an, again, working within this same partnership between PML, Plymouth and the MBA, Marine Biological Association, but also incorporating local city council and the University of Exeter. Is a new initiative, fairly new initiative, sorry, Smart Sound Plymouth. And that's really where that's kickstarted our interest in the marine autonomous sector, particularly around the shiny yellow robot end of what we do that many of us are familiar with, but also in terms of the communications network and the background, the back end data and communications requirements that sit around that, achieving that level of capability. So within that initiative, we're developing a motor platform capability with an aspiration towards a fully integrated marine monitoring framework. And we have between that partnership, we have a whole host of different vehicles and different levels of capability, also incorporating a variety of, as I mentioned, back-end, including artificial intelligence and machine learning capabilities to achieve a number of different science aims, which I'll come on to explain in a little bit more detail in a moment. Non-intrusive seabed monitoring tools, underwater positioning, and now stretching into underwater comms and above water comms capabilities, an ever-growing library of AI and machine learning identification tools and training data sets, and a whole host of different technology development processes. And I think a key part of what we're doing also is building those regional, national and international partnerships. So to try and dig into the detail a little bit more, part of that investment has included a fully capable full 4G and in some areas 5G capability in our coastal environment. So this has been a partnership with Vodafone and Nokia to deliver that private marine communications network to Smart Sound that we can make available to partners. It's particularly useful in terms of obviously getting some high data returns in terms of communications back to shore, making things like video, transfer of video, live video data streams particularly achievable. And we're also working towards things like transferring of large image transfer from some of our autonomous systems, autonomous sensors. We've also extended that to enable remote operation centres that have started to provide some over-the-horizon piloting capabilities within our Plymouth Sound and Western Channel Observatory environment. In fact, only in the last few days, partners at the University of Plymouth have achieved an over-the-horizon transect between the city of Plymouth all the way to our offshore buoy stations, as I mentioned earlier. We're now extending that above surface comms network to a subsurface capability. We've had recent investment in a subsurface marine comms network using acoustic network. It's really interesting to see the last talk and how we can potentially expand upon this level of capability. Really nice to talk to people who are potentially extending that capability. In our first step, though, in this space, we're extending this to an acoustic network that will work alongside our above surface comms network, using our uncrewed surface vehicles, fixed buoys, our fixed smart buoy capability and drone capability to better augment or better improve really our submarine vehicle capability, including gliders, mini subs, and AUVs. And I think in terms of a bit of an advert for partnership, they're obviously providing this as a continuous basis. This is, like I say, a sustained observing system that's been in existence for many decades. That's provided that the expertise, the people, and the tools that provides an extremely accessible coastal ocean observatory framework. I'll be really keen to hear from any of you who are keen to sort of reach out and use this as a potential testbed or a future future demonstrator for some of the technical capabilities. And lastly, around the Smart Sound Plymouth capability is that strong triple helix cluster that, again, Professor Sharma mentioned earlier, which I say it's triple helix is because it's built on the academic, government and industry partners who have this collective, actually provides the largest marine autonomy cluster within the UK, and provides us very easy and open access to many of our industry partners. So, as I said, the thing I actually wanted to come back to today was what our newly launched initiative that sort of benefits and builds upon some of those longer-standing capabilities that we've been developing under Marine Research Plymouth, and that's the National Centre for Coastal Autonomy. And I think the aspiration here really was born that there's a lot of work, obviously, in the marine autonomous fields. We've been hearing over the last couple of days about some of the great work people in that space. But there's and certainly within the type of ocean research that I do, there's a recognition really that the coastal environment is often not as well serviced as some of the open ocean applications. And that's particularly the case, in my opinion, for some of the submarine activities. We see ever deeper, ever longer range capabilities being developed within our AUV capability, for instance. The glider fleets that are growing at an exponential rate around the world aren't necessarily particularly well served to doing the type of coastal ocean research where things like close proximity of coastal hazards, rocky shorelines, and shallow water and strong tidal environments. So the focus here really is to try and provide a centre of excellence built upon that great sort of coastal ocean research capability that exists in Plymouth to provide a centre for specifically focused on coastal autonomy. So just to round off my talk really today, I have recent examples of some of the work that we're doing in that space, focusing on smart coastal observing systems, autonomous image and classification systems, and ending on a demonstration for a CBRS mapping exercise with uncrewed surface vehicles. So this first example is one that I was personally involved with, which featured underwater submarine gliders, the sloping type that many of you no doubt are familiar with, and using that to try and improve the operational ocean forecast capability with a complex coupled hydrodynamic and ecosystem model. So the fine scale NEMO and ERSIM ecosystem model, ERSIM having been developed at PML, some of you may be aware of. So in order to actually achieve the optimization of the flight and provide that smart pilotage capability with the vehicle, however, we also included a stochastic prediction model. This was work done by partners at Exeter to then provide feedback to the glider to present its next day and future day missions, which were continually iterated based on the real-time data or near real-time data coming in from the glider, Earth observation data being assimilated into the operational forecast model, and then essentially learning and training the prediction model to understand where best to send that glider next. And this work is summarized. I'll provide the there's a reference at the bottom there that you can follow up on all the details of this, but just to try and present some of those results. In the first instance, looking at just the operational area. I don't know if you can see my cursor, but on the top left as you're looking at the screen is the operational area close to Plymouth. And we worked within a fairly tightly constrained box, not least because this is a particularly heavy shipping area. The English Channel is one of the busiest shipping lanes on the planet. And we also have a lot of commercial ferries, commercial shipping, ferries, fishing, and military exercises coming out of the Plymouth region. So we needed to be quite constrained within a certain area. And so we had to get it right, essentially, with these predictive model capability. The bottom slides there on the left just show where the operational model was actually getting the results significantly wrong. So this is the difference, essentially, between what we're observing with our glider and what we're actually predicting within the operational model. And then if we look on our right, on the line graph there, firstly, we see the light blue color, which is the scatter, the real-time data coming in from that glider, which is not being recreated in any of our model realizations. But if we take the daily mean of those data, which is the dark blue line, and first of all look at what the operational model is actually trying to achieve there, which is the dark green line, we can see that the operational model, and we can see where that failure is occurring. It's massively under predicting the amount of chlorophyll signatures within those coastal waters. That's not too surprising. We also compare it to the ocean color, the Earth observation data coming from satellites, which is also being used to constrain that model. And we can see that that's also significantly under predicting. So it's no great surprise that that state-of-the-art operational model isn't necessarily achieving what we're observing on the ground or in the water. If we then look at the results though coming from our stochastic prediction model, the purple dots there, we can see a much better realization of that real world data as being observed with the glider, and our offline version of the operational model, the AMM7 campus, which is this orange line, you can see is having a much better, doing a much better job of achieving that capability. So this was a fairly simple, well, it wasn't simple by any means. It was a short-term single glider, 3-month deployment, but used as a test bed really to try and be as a preemptive experiment really towards large fleet control in order to actually better optimize our operational model capability. And that really is how we see this work going forwards. And I'd be really keen to talk to people who are taking similar routes or approaches or alternative regions to achieving that, that might be working towards digital twin coastal ocean applications, where I see this as a particularly useful tool. My second example is very different to that. This is now using a fixed sensor, but in this case, the automation comes through the imaging and classification of plankton images. So traditionally, Plymouth Marine Labs maintains their plankton time series by going out, collecting samples from the vessels, and then taking that back to the lab where they undergo different types of analysis, depending on what size classification they might be. So, as with the majority of the community at the moment, we're starting to get very excited about the new instrumentation coming online and some of the autonomous machine learning capability that allows us to potentially autonomously recognize and classify some of those images. In choosing that instrumentation, we've settled on 2 particular instruments to try and give us the maximum coverage for the type of phytoplankton that we see within our environment here, working within the phyto and zooplankton range covered by the IFCB, that's the McLean Image Flow Cytobot, and the Plankton Analytics PI10. It's a fairly new project, this. We've recently taken possession of that equipment. We're currently doing tests in the labs and preparing the mooring to be able to accommodate that in the very near future. And in the first instance, we'll have that as a 2 mooring setup with the IFCB and the PI10 on separate moorings, and with the eventual hope that we'll get this all of that system working on a profiling, autonomously profiling winch coming from a new buoy that we've bought and is soon to go out into our L4 station. And there's a lot, but before we can even get to that autonomous identification and classification, there's a lot of work already going on in order to actually achieve the mechanical requirements of that experiment. So it's a watch this case, but I thought that might be of interest to a number of the people in the audience today. I'd certainly encourage or ask for anyone to reach out if they're particularly interested or already underway undertaking plankton identification classification exercises, and there's a growing community in this space, and I'm really keen to start seeing how we can each learn from each other. And my last example today is one that was actually developed by partners at the University of Plymouth. This work led by Dr. Tim Scott, and this is a USB uncrewed surface vehicle-based seagrass mapping exercise that employs some deep learning algorithms, with the ultimate aim here of providing autonomous capability towards a natural capital or blue carbon assessment. So in this instance, using one of the fleet of uncrewed surface vehicles that we have collectively across the NCCA partnership, Plymouth University here using this twin hull USV provided by Hydroserve. It has a relatively fast speed of about 2.5 knots and provides some endurance of beyond 9 hours, and can be remotely operated directly and also provides some autopilot capability, and I'll come on to show some examples of that in a moment. Just to provide some quick results, early results from the single beam Veilport altimeter there, you can immediately see that the immediate returns, if you like, from this sensor gives a really nice strong signal where we get this very strong back return from our seabed, and then this rather fuzzy and difficult to interpret return from the sort of variable meadows and field seagrass. The team at Plymouth then used machine learning algorithms similar to those used for electrocardiogram analysis to try and identify and test the ability to identify and classify the seabed type, and then also to identify the height of those seagrass meadows themselves. And they're achieving a really impressive level of skill here, up in the sort of 94, 96% level capability. And the applications of this, just to demonstrate one recent field trial. This is a 3-hour expedition with the USB, achieving in excess of 12 kilometers area, not far from the Plymouth Sound area that I showed you earlier. And we can see the useful application of this type of approach in that we can fairly rapidly do these rapid sample capability over relatively large areas, and in this instance to look at the spatial and temporal variability in those seagrass and seagrass meadows in this area. And there's a number of different field trials going on in different coastal locations as a result of this work. So I'm not quite sure. I apologise, I've not been tracking my own time. I hope I've stayed within the allotted time, but would welcome any questions on the NCCA or other activity we're doing in Plymouth. But also, please, if you want to just reach out to me directly, there's my email on that slide. Thank you.